So NSEM Viva is scheduled to Friday, Saturday, Sunday, similar to mid-sem Viva, and it is from 3 to say 8 or something. So any comment, any suggestion, anything?
Sir, can we talk about this at the end of the class?
Syllabus, do you asking? No, what do you ask?
Sir, I am saying, can we tell you about this at the end of the class?
Why?
Sir, everyone give their feedback, then we can tell you.
Oh, in the meantime, you will discuss. So that you mean to say.
No, sir. I'm not saying that. I'm just saying that everyone join the class and then they will tell. Mm,
Those who did not join, let them not to tell.
okay, sir.
Sir, sir,
Yes.
I am coming back to campus on 19th, so my roll
So
number is 4. So
yes.
can
So
I get
you
Viva
mail
on
me.
21?
So you mail me accordingly. I'll fix your Viva to 20.
Yes, sir.
So this is the individual cases. So individual case you mail me. So there is no issue.
Okay, sir.
Hmm. Okay. So let's start the class now. So as of now, we are reading the. Now you can see the full screen. So you are reading the displacement sensor, and almost many displacement sensor we read, and this is very important thing to know. So last class we read the seismic sensor, which is used when there is no fixed reference frame, you know. So now we'll move to piezoelectric transducer. This is also very important transducer or important sensor, which is used for measuring displacement. So now, please listen carefully. So the piezoelectric transducer, you know that most of the cases, the name suggests itself the operation, principle of operation, and many things. So here, if you see the name is piezoelectric, right? So name suggests many things. So when certain solid materials, this is not property of all solid materials, some solid materials, a few solid materials, when they are deformed, they generate electric charge. Okay. So piezoelectric, that means generation of electric charge by means of pressure. So when these solid materials are deformed, few materials, not all. If you take iron rod and then deform it, it will not generate electric charge, definitely. So a few materials, solid materials, when they are deformed, they generate the electric charge. So this effect is also reversed. What is the meaning? Means that I am saying that if they are deformed, electric charge will be generated. This is the effect is reversed. That means if you give some electric charge, or if you give EMF, or if you apply an EMF, the material will mechanically deform. Okay, so the material will respond by deforming themselves mechanically. So this effect, when you uh, some solid material deforms when you apply when you deform some solid material, it generates electric charge. Reversely, when you give electric charge or EMF, these materials get deformed. So this effect is known as the piezoelectric effect. Okay. So first, before knowing that piezoelectric transducer, you need to know the piezoelectric effect. So this effect known as the piezoelectric effect, and the materials which exhibits this effect is known as the piezoelectric material. So it is clear. So what is piezoelectric effect? It is clear. When some solid materials are deformed, they generate electric charge, and reversely, when you give electric charge, those solid materials get deformed. So this effect is known as piezoelectric effect, and the materials which exhibits this effect is called the piezoelectric material. Now, as an engineer, we need to see that if we can use this certain effect, which is a very important phenomena in our application. Definitely, it can be utilized in many applications. So we'll focus as a transducer or sensor application. But if we don't, if we broadly say that this can be utilized in many applications, such as high voltage, low current electric power, and the spark ignition. Okay, what does it mean? So, no doubt it can be used as a transducer. I will come to it in a detailed way. This can be utilized in many applications such as high voltage, low current electric power generation. So, electric power and spark generation. So if you give very high electric voltage, this material will get deformed. Similarly, if you deform it, it will generate voltage, and that can be very high voltage, low current. It does not mean high voltage means always it will give shock, damage, not like that. If the current is very low, then there will not be any damage as such. So it can also be used as a spark generation. Okay, and definitely it can be used as a transducer, which can measure the displacement, which can measure the velocity, which can measure the acceleration. Definitely it can measure the force also, it can measure the pressure. Okay, so pressure transducer, force transducer, displacement, velocity, accelerator, all those type of transducer can be used using piezoelectric materials. Now, if you ask that, sir, what is piezoelectric material? Can you give some examples? Definitely, you need to know some example. There are some natural piezoelectric materials. That means those materials can be found in nature naturally and shows the piezoelectric effect. Such materials can example of quartz. Quartz is a very good example of piezoelectric, natural piezoelectric material. Rochelle salt is also a good example. Now there are some synthetic materials which are synthesized and it is shows the piezoelectric material. So lithium sulfate. Lithium sulfate is also can be stated as a synthetic piezoelectric material. Uh, you can see that the polarized ferroelectric ceramics, okay, such as the barium titanate, that can also be uh, used as a piezoelectric material. There are polymers. There are many polymers which shows the piezoelectric properties. Okay, so and few polymers are sold in market also. Okay, they shows the piezoelectric property. Now, tell me up to this if you have any doubt. So we discuss what is piezoelectric effect. We discuss what are the different application areas. We discuss what are the particularly different materials which shows the piezoelectric effect. Okay. Okay, if you have no doubt, let's proceed. Now, let us try to consider some practical things. Let us consider that we want to make a transducer out of a piezoelectric material. Suppose we took a piezoelectric material, or I gave you a piezoelectric material. I say that you built a transducer out of this piezoelectric material, and that is your class project. So what you will do? Most of the student will not do anything. Okay, let's don't consider this. So those who will try to do something or try to build a transducer out of the material I gave to you. So if you think, that means you need to either apply the voltage so that you get deformation and you use that deformation, or you deform it and you measure the output voltage. For example, some basic conceptual thing can be, suppose I gave you a piezoelectric material and I ask you that you uh, use this material as a displacement transducer or force transducer. That means you need to apply a force, and then it might be displaced or say pressure, and then you will get some output voltage, and out of that output voltage you will measure the output voltage and you will calibrate, and you can tell me that this much is the input force or pressure. This is the main basic thought process. Now, if you come down from thought process to manufacturing or to building something, now the point is coming, how do you get the voltage? So if you directly apply an wire to the piezoelectric material, you will not get the voltage. Okay. So what you need to use some mechanism which we call the electrode. So you need to build an electrode on the surface of the, now you see the electrode. So you need to build an electrode on the surface of the piezoelectric material, and then you attach a wire with the electrode and two wires, and you measure the voltage difference between the two wires. You measure the voltage, you calibrate it to force or pressure or displacement, whatever. So this is the main concept. Okay. So then what do you need apart from to get the output voltage? You need to implant an electrode, right? So on the surface of the material. So I gave the material, so you need to implant an electrode on the surface of the material, then you can use the material. Now the point is, here are 2 points. So electrode must be compliant. What does it mean? So it means that suppose you are deforming the material. So suppose you apply some electrode and then you are deforming the material. So if electrode is on the surface of the material and you are trying to deform the material by applying force or pressure, then electrode can also be deformed, and as a result electrode can become a discontinuity can happen in the electrode, and if discontinuity happen in the electrode, you will not get any output voltage. So you need to build an electrode in such a way, when you apply the pressure or force, then the discontinuity should not happen. Okay. So that type of electrode is called the compliant electrode. So we call the electrode must be compliant. So you have to build an electrode on the surface of the piezoelectric material, and that electrode must be compliant. Okay, it means that during the deformation, the continuity of the electrode should not be broken, or the continuity should be maintained during the deformation of the electrode. Okay, so you deform the material, electrode will also deform, but it will not break. This is called the compliant electrode. Then you attach two leads wire as you have seen, and from the compliant electrode, and then you try to measure the voltage when you apply some force or some pressure, whatever it could be. Now tell me if you have any query. Detailed discussion we are doing. So this type of in-depth thinking you need to do. Do you have any query? Okay, so let's proceed further. So now the point is, so maybe the voltage. So you may think it that as when you are giving a mechanical force or mechanical motion, some charge is getting generated. Definitely some charge is getting generated. Now you can think this as a capacitor. You see there are two electrodes, inside there is some material, and you are getting voltage out of. You can think this is a capacitor or and a charge generator. Okay. So due to the deformation, it generates its charge and it stores the charge and it produces as if it is a capacitor, and it gives some voltage output. Now, one thing I did not mention, I should mention that earlier, that the charge polarity, when charge is coming, EMF is coming, the polarity is important. So there will be some polarity. So suppose if we apply the force Fi in this direction is shown in the figure, then there will be a polarity. And then if you try to, instead of keeping this, you try to give it opposite direction, then the polarity will be reversed. So polarity of the generated charge or polarity of the EMF depends on the direction of the force. So if the direction of the force is reversed, the polarity will also be reversed. So then by refined way, I can say that the tension, or I mean the direction of the force with the direction, produce a definite voltage which is proportional or could be proportional. I'll come to that whether it is proportional or not. And the polarity also is associated with the direction of the force. Okay. If the force direction is reverse, the polarity of the charge generator or voltage will be reverse. Now we consider some force is applied as it is shown in the figure to a piezoelectric material. Now, if we think about that, what are the type of force can be applied? So if you think there might be two types of force, one is linear, another is torsional. So if you see the axis, which is figure A, there are three axes, 1, 2, 3, and the force, whatever you apply, can be along the three axes, or it can be um, decomposed into the three axes. And so the force is three axis. This is the whatever you are thinking, that linear force. Apart from that, there might be some torsional force. That means the bending force. So you see that 4, 5, 6. These three are the torsional force. It is given. Okay, along the three axes. Here we consider only the linear force. So 4, 5, 6 we will not consider. We think about only linear forces applying and what will happen to the piezoelectric material, how we will get the output, and how the output is related with the force and all, so that we can build a transducer. That is our objective. Okay. Now tell me if any query up to this point. Okay, no message in chat box. Nobody is asking anything. Let's proceed then. Now, so when you say that whether when you apply some force, generate two main constant, okay, constant and d constant, okay, which is named as the g constant and d constant. So what is the three? Okay. This is the same thing twice pasted. Sorry, remove once. Okay. In the direction 3 divided by the force applied in the direction. So if you ask that what is the name, actually it is called d constant. Okay. So it is used to relate the force with the generated charge, and the d constant can be defined as the charge generated in direction 3, which you can say q, and the force applied in the direction 3, which is fi. Now, if I ask what is the d constant d11, that means it is a charge generated in direction 1 divided by the force applied in direction 1. Okay. So then it will be q by f1. Here it will be q by m. If I D33 and G33, they both are dependent, but then let's know that what is G33. So G33 or G11 or G22, so it is a G constant. Okay, what do you mean by the G constant? Suppose G33, that means that the field produced in direction 3, that is the field produced in direction 3 divided by the stress applied in direction 3. Okay, so if I say that the G33 is the field produced in direction 3 divided by the stress applied in direction 3. Now suppose if you see here, first figure again. So what is the field produced in direction 3? So E0 is the output voltage, and you see that the direction 3 is the perpendicular, T is the thickness. So field produced in direction 3 will be the EMF by the distance. So it will be E0 by T. Now, what will be the stress applied in direction 3? You see that the force is Fi and force divided by the area. The area you see W is the width, L is the length. So area will be WL. So stress applied in direction 3 will be Fi by WL. Okay. So now if you see that G33 is coming E0 by T divided by Fi by WL, and then that is coming E0 by T divided by Fi by WL, and if you do it, so it will be E0 by T into WL by Fi, which is the G33 constant. Okay. Now here you see that if you know the constant G33, T, W, L, Fi all are known, and G will be known, and you can do experiment and you know the G, and G will be known definitely for the particular material. Then you can calculate E0, the output voltage. Here again, I am emphasizing, you see the formula G33 will be E0 WL by TFI. So now if you see that G33 is known, or G22 is known, or G11 is known, for the simplicity, I am taking only one directional force at the direction of 3. So G33 is known, and what T is known, because whatever the cube or whatever we are taking, the dimension will be known, W will be known, L will be known. And if G33 is known, you can measure the output voltage E0 and you can tell what the Fi or the input force is. Okay. Reversely, if we know the input force, we can calculate the output voltage. Okay. Now this is a G. You have seen that the G constants are to relate the output voltage with the force applied. Now, if you want to relate the charge produced with the applied force, then whatever I discussed, D constant will be important. So it will be Q by Fi. So D constant is to relate the charge with the input force, and D constant is to relate G constant. Sorry, G constant is to relate the EMF and input force. Now you might think that whether and D, there are two constants I am discussing. So you are might be thinking whether G33 and D33 are they independent? In fact, no. It should be noted that G33 and D are not independent.
Hello, sir. Hello, sir. Hello, sir. You are not audible.
Sorry, I was disconnected, so there is some internet problem. Okay, so again I'm sharing my screen. So now you can see my screen.
Yes, sir.
Okay. So what I was discussing, that G constant and D constant both are not independent to each other. So that's what I was saying. So how we can relate G constant and D constant to each other? So we have seen that G33 will be equals to E0 W L by T Fi. Okay, because G33 will be defined as field divided by the pressure or the stress. So E0 WL by TFI. So, but we know that the capacitance, so these two are related in terms of capacitance. But we know that the capacitance C will be equals to epsilon WL by T. So we can replace this WL by T with the C by epsilon. So our G33 is becoming E0 C by epsilon Fi, and we know that E0C is the Q charge, so Q by epsilon Fi, and we know that Q by Fi is D33, so it is D33 by epsilon. So D33 will be equals to epsilon G33. So D33 will be equals to, so it is the dielectric constant multiplied. So G and D both are related with the dielectric constant. Okay. So is it clear, or you want to tell me again? I think it is not required. It is very simple. Okay. So now let's proceed further. Now how we can use, we need to go more practical situations where this can be used as a transducer, what I was telling. So when you use as a transducer, we have a crystal, we have a compliant electrode, we have two cables, so we have two um, port coming out of these two compliant electrodes, and then we have a cable and we have an amplifier. We get the output from the amplifier. Because the output voltage is very small, you cannot measure it really, so you need to apply one amplifier, and from the amplifier you will get some output, and that you can measure. So this is the full construction. So when I give you some piezoelectric material, so you have to do a compliant electrode, which we did in our lab actually. Some of your friends in earlier, they did some project. Okay. So compliant electrode, and then some cables are coming. We have an amplifier, and output of the amplifier we'll see. So with this above background, we can proceed to analyze this one. Okay. So you consider that some force is given. When some force is given, some displacement xi is happening, and that is creating some voltage output which is going through the cable, and then we have an amplifier, and then we are getting output of the amplifier. So here, as I said, that force can be, it can be used as a force transducer, pressure transducer. Also, it can be used as a displacement, the xi, which displacement it is getting, displacement transducer. Okay, and if you know the displacement, velocity can be measured, acceleration can be measured, and definitely pressure and force can also be measured. Okay, so now let's see that how it can. So the figure A is the full diagram of how a how you can use, you can construct with the a transducer from a piezoelectric material. So we have a crystal, we have a cable, we have an, now we need an equivalent electric circuit. Okay, without that we cannot proceed. So you see that the equivalent electric circuit, you see the equivalent electric circuit, that is a charge generator Q. So crystal can be replaced by a charge generator. And because crystal is now coming as a capacitance, it's generating charge, and then charge is getting leakage. So we can think about the crystal as a charge generator and a leakage resistance parallel to it, and a capacitor. Okay, so these three things, okay, is consisting of the crystal. So we have a charge generator which is
Yes,
KQXI.
sir.
Yes, sorry.
Sir, sorry to interrupt, but the slides are not changing, sir.
Oh, I see.
I
So,
tried to rejoin and I was not able to see the screen also.
oh, so this is the case for everybody.
Yes, sir.
Okay, so then I am stop sharing and then sharing it again.
Yes, sir.
Hmm. Oh, I see. So now can you see my screen? It is number 1110, slide number 1110. Can you see my screen?
No, sir.
No, sir.
There is some. So wait, I'm changing to my internet connection. There is some issue, poor internet connection or something. So I'm trying to use my hotspot. Then let's see. So now again I joined. Let's see. So tell me, can you see my screen and slides? Can you see my slide number 1110? Anybody can respond?
No, sir.
What is the problem? So I'm trying to share it again. Stop sharing. Again trying to share. Can you see it now? Can you see my slide number 1110? Please respond.
No, sir, not yet.
No, sir.
Till no? Can you see my screen?
No, sir, it is not visible.
What is the problem? Network is looking fine. Again, I'm trying to share. Tell me if you can see this.
No, sir, your slides are not visible.
No, that is fine, but you can see my screen.
No, sir,
Now
I
can
don't see anything.
1110?
So your screen is not shared.
Screen is shared.
Sir, but only the logo is coming, sir, like SB, that's it.
Only.
Only logo is coming.
So let me try to. Now can you see it? Slide number 1110. You tell me if you see it or not. Now network is showing full and everything is fine. Probably now you cannot hear
Due
me.
to some glitch in Microsoft Teams.
Yes. So now network is perfectly fine. It's
Yes, sir.
not coming, na?
Not coming, sir. Sir,
Okay.
maybe you can start
Yeah.
another meeting and we'll quickly join there.
Oh, another meeting can start.
Maybe.